Okay, so today we do logarithms, and logarithms are something that you've had some before. And I think that most of what we get in today's lesson is mostly stuff you've had before. It's the stuff that follows is probably where you didn't go if you had it in Algebra 2. And we'll see what a logarithmic function is and where they came from and why they're important and things like that. So logarithmic functions are a different way to express an exponential. It's the same relationship, it's just reordered in a different way. For example, 2 to the third equals 8, right? With logarithms, you would write that same relationship as saying the log base 2 of 8 equals 3. And we'll talk in a minute about why would we do this. There was a real reason we did it. It's very important in the history of science, the fact that they came up with this way of representing this relationship. Right? Things to notice about exponentials and logarithms. Right? We've already dealt with the base of an exponential. Right? That would be, in this case, 2 was the base. Well, this number that's right after the letters LOG, that's a little bit down as like a subscript, right? That's the base of the logarithm. So they both have bases, and they're the same, right? Bases. Okay, now in the reordering of things here, notice that the logarithm equals, and look on the other side of the logarithm, what does it equal? It equals what was the exponent of the exponential, right? So this is exponent. Right? Now, the thing that our exponential equals 8 becomes the argument of the logarithm. An argument is just that's a general term for anything you put inside a function. I don't have a better name for that, but this is the argument of the function. Once you've put the 2 and the 3 in the right place, there's only one more place for anything to go. So the 8 goes inside the logarithm. So saying 2 to the third equals 8 is the same thing as saying this. Generally, when you're talking about a log, let's say I said log base 2 of 8. In your mind, what you're thinking is, what power would I raise 2 to get 8? 3. That's the logarithm. So let's go back and forth a couple ways. There's going to be some homework that are just like this, right? How could I rewrite this exponential as a logarithm? 2 to the 5th equals 32, right? And what would be the base of the logarithm? So whatever the base of the exponential is, so that's a 2. Right? And what does the logarithm equal? The exponent, right? So what's left to go inside the logarithm? 32. So log base 2 of 32 equals 5. Or, again, if you cover up the 5 and just had to evaluate that, you'd say, what power would I raise 2 to get 32? The answer is 5. Okay, try the next one. Let's go the other way. If log base 3 of 1 equals 0, then write the exponential. What's the base of the exponential? 3, right? And what is the exponent? Remember, the logarithm equals the exponent. And so what does it equal? 1. Okay, so 3 to the 0 is 1. Remember, that's a property of exponents. Anything to the 0 equals 1, which tells you that the logarithm of 1 is always 0. Those are two different ways to say the same thing. How about this? 4 to the 1/2 equals 2. right? That's like saying the square root of 4 is 2. What would the logarithm look like? The log base 4, right, the base of the exponential, of what? Of 2 equals the exponent. Logarithms equal exponents. Okay, and the last one, we'll go backwards, right? What is the base of the exponential? The base of the exponential? Come on. 10, right? Whatever's the base of the logarithm, that's the base of the exponential, right? What is the exponent of that 10? Negative 2 equals 1 over 100. Again, 10 to the negative 2. The negative exponent tells you would flip that to the other side. It would be 1 over 10 squared, and 10 squared equals 100. So that's true. What's I going to say about that? I'm forgetting. It'll come up. Okay, so let's try to do, so these are actually the same relationships right there. So again, you'd say, what power do I raise 2 to get 32? 5. What power do I raise 3 to get 1? 0. What power do I raise 4 to get 2? 1/2. What power do I raise 10 to get 1 over 100? Negative 2. You good? Good. Emily, you okay? So bottom line, logarithms are exponents. So the properties of logarithms, which is the next lesson. Well, I shouldn't quite say that. There are some properties we're going to get to right here. The properties of logarithms are properties of exponents. Meaning, if you remember, properties of exponents would tell you that if you're multiplying two exponentials with the same base, 10 squared times 10 to the third, that in the end, you could write that as 10 to the 2 plus 3. You add the exponents. 10 squared times 10 to the third is 10 to the fifth. Okay, well, with logarithms, it works similarly, right? If I wanted to find the logarithm of 100 times 1,000, we actually can use properties of logarithms and split that up into the logarithm of 100 plus the logarithm of 1,000. And by doing that, by taking advantage of the fact that logarithms are exponents and these kinds of properties work with logarithms, it actually allows us to turn multiplication into addition. Right? A multiplication problem now is an addition problem. We just have to identify all of the exponents, i.e. logarithms, for a whole bunch of numbers that all have the same base. And then we can convert all of our numbers into the logarithms and add them up. Well, that was really important. In 1609, when they invented this stuff, a guy named John Napier invented this stuff. You could imagine how hard it was to do calculations at that time. They didn't have calculators. They didn't have computers. And they were actually on the verge of discovering things that required a lot of calculations. I mean, if you think back, 1609 was after Copernicus said that the sun is the center of the universe. It was after the invention of the telescope, but it was before Galileo got in trouble for saying that the sun is the center of the universe. But we were doing lots of observations of the skies and the stars and that, and trying to come up with relationships, that are out there. But think of the numbers involved. Think of, once we start trying to estimate the distance from the Earth to the sun, you're talking huge numbers, right? Think of trying to estimate the area that's swept out by a planet that's revolving around a distant sun. If it's a circular orbit, you got at least pi r squared. The area of a circle is involved there somewhere. How are you going to do that calculation? Well, this is how they learned how to do these calculations. It's not a coincidence that after that time, in the next 100 years, that we discovered things like the Earth's orbit around the sun is actually not a circle, right? And they were able to figure that out by doing these kinds of operations and understanding why, things weren't just quite right if you describe that orbit by a circle. It's actually an ellipse. It's a little bit longer in one direction than the other, right? The guy who discovered that is a guy named Kepler, and that was like later in the 1600s. But, we still didn't have the advantage of any technology here. All we had are logarithms. Okay. Now, if it was just for logarithms, for calculations, we wouldn't need this anymore because we have ways to do this. We do have calculators and we do have computers to do this stuff. But actually, logarithmic functions are important in science too. There's a lot of relationships that if you're trying to model with a math equation or a math function, they're logarithmic, and you need that kind of function to approximate it with a model. See what's next. Okay, so the first logarithms that they came up with were log base 10, which kind of makes sense for our culture and society, right? Because we count in base 10. Right? Everything we do is in base 10. So what they did, they made big tables of numbers where for every number, they would give you the exponent that 10 would be raised to equal that number. And that one is called the common logarithm. Common logarithm means log base 10. And it is, I shouldn't say it's so common, but understand that if you see a logarithm like this that does not have a base, you assume that they mean log base 10. Common logarithm is log base 10, usually is not written with a base. It's just assumed. Just like you assume x is raised to the first power here, right? Or that a square root has a 2 in the hook, right? There's things that we just assume. So log base 10 usually just looks like log x. Now on your calculator, you have a log base 10 button, which is right here, right? The one that says log without a base, that's log base 10. So, I mean, it's simple to use. If you wanted to take the logarithm of 275, you just hit the log, okay, and then put in the 275. So you would raise 10 to the 2.439 ... power to get 275. Well, that kind of makes sense because 10 squared is 100, and 10 to the third is 1,000. So in between 100 and 1,000 is this 275. So we're getting an exponent, which is in between 2 and 3. It makes sense. Try to do the log of -1/2. Now, if your calculator is set to A plus BI mode, which it might be, then you want to go back and change your mode. Quit. Change your mode to real. If your calculator was in real mode, then you got what I got, which was an error, right? Which is going to come up later, but logarithms do not have a domain of all real numbers. You can only put certain values in for x, right, when you're evaluating a logarithm, which makes it the third restricted function that we've got. Because remember, we cannot divide by 0. That's one thing. We cannot take the square root of a negative number. There's another restriction on what you can plug in. And now we're going to learn that you can't take the logarithm of a negative number or 0 either. So that's 3 different functions that we got to be aware of what we can plug in. Okay, let's see. Okay, so here's the beginnings of properties of logarithms. I mean, these are probably these are important, but we do 3 more properties in the next lesson. But these are the big ones at the beginning. We've kind of already seen the first one, right? In every one of these properties, they're giving us that relationship as a logarithm, and then they're giving it to us as an exponential. Like log base A, and base A means any base. Equals log base A of 1 equals 0, right? Well, if I rewrote that as an exponential, that would be A to the 0 equals 1. And we know that already. Anything to the 0 is 1. So that's not doing anything else except re-expressing a relationship we already know as a logarithm. Okay. Right. The next property, the log base A of A equals 1. Meaning if you put inside the logarithm the base of the logarithm, you get 1. Which, again, if I convert that to an exponential, you know, the base of the exponential is A. It's A to the first power equals A. That's what that says. It's an exponential, and that's obvious, right? A to the first equals A. That's all this relationship says here. Okay, more important, right, is this relationship. The log base A of A to the X equals X. Meaning, if we take the logarithm of an exponential and the base of the logarithm matches the base of the exponential, then the bases cancel each other out. The logarithm cancels with the exponential, and all you get is X. And you could actually flip that relationship. If you take A, the exponential, to the log base A of X power, then the A log A cancels each other out, and all you get is X. So those are our properties, the main ones. There's also this thing at the end, which is like we did in the homework last night, which is a one-to-one property for solving very simple logarithmic equations. Right? If you have a logarithm equals a logarithm, they have the same base, then it must be what's inside the logarithms are the same. Right? If log base A of X equals log base A of Y, X equals Y. Okay, look at this one here. Simplify log base 9 of 9. Which one of these properties would be used? 1, 2, or 3? Log base 9 of 9. 2, right? Log base A of A equals 1. So that's the second property. Right, that's this one. How about the next one? 20 to the log base 20 of 3. Which property does that look like? 1, 2, or 3? Say again? It's the second half of the number 3, right? A to the log base A, that's like saying 20 to the log base 20. Right? Same thing. We just said A is 20. Okay, so what would this one equal? 3, right? Whatever's inside the logarithm, right? 20 to the log base 20 of 3 is 3. Right? That's this right here. Okay, how about the last one? The log of the square root, the log of base square root of 3 of 1 equals, which property is it? Okay, the log of any base of 1 is always 0, right? In this case, our base is the square root of 3, which is a very odd base. We'll probably never see it again, but it's just to make the point. It doesn't matter what the base is. You take the log of 1, you get 0. That's this one right here. Okay, so now we've got, this is the one-to-one property, right? We've got a logarithm equals a logarithm. The base of the logarithms are the same. So what equation can I set up? Right, if the log equals the log, then the arguments of the log have to be the same, right? Because everything else about this is the same. So you're going to set up x squared plus 3 equals 12. Right, that's here and here. Right, no reason for the logarithms anymore. We just set the arguments equal to each other and solve. X squared equals 9, x equals plus or minus 3. That's one-to-one property. Good with that. We're done. Slow me down if I go too fast. Okay, now, let's find the inverses. Remember back, it wasn't that long ago, because we just did inverses before we did that 9-week test. What were the steps to find an inverse? We got f of x equals, the first step was, say again? Change it to a y, change the f of x to y. And then what? Switch the x and the y. Right? And then what? Solve for y. Well, here's the thing. We don't know how to solve logarithm equations yet. Okay, so what we can do is we can convert that to an exponential. What would the exponential look like? What would the base of the exponential be? Say again? The base of the logarithm is the base of the exponential, right? The logarithm equals the exponent. And what goes on the other side? Y. Right? So we converted that to an exponential, and by doing that, we did solve for y. Right? We got y isolated on one side, and the inverse must be the other side. Okay, there's one last step, f to the minus 1 of x equals a to the x, which tells you that exponentials and logarithms of the same base are inverses of each other. Right? Exponentials and logarithms are inverses, which is important. That's why they're taught together, because we need one to solve the other. Right, so if I start with f of x equals 2 to the x, the exponential with a base of 2, then the inverse would be log base 2 of x. So now all the things that we already know about inverses are true about these two functions. Remember, by switching the x's and the y's, it's like switching the domains and the ranges. Right? So the domain of this exponential function, which we know is all real numbers, is the range of the inverse. So the range of a logarithm is all real numbers. If you remember, the range of an exponential function is the domain of a logarithm. Remember the exponential function, right? The exponential function looked like this. It did not have an unlimited range. It had an asymptote on the x-axis, and all the values were above that. So we would have said the range is y greater than 0. So what does that make the domain of the logarithm? X greater than 0. That's why you can't take the logarithm of a negative or 0. And then the last thing is we know that graphs are symmetric with respect to the line y equals x. They should look like they're flips across that line. And I don't know if I have it on coming up or not. But the other thing that we know, and this comes from our section on inverses, is we know that f, if you take the composition of a function and its inverse, doesn't matter what the order is, whether you do f of f minus 1 or f minus 1 of f, they will cancel each other out, and all you're going to get is the x. Right? We've actually already seen this in the properties that we saw. I'm going to go back when everybody's done with that. We done? If you go back to those properties that we had, right? That's what this number 3 is, right? This is the composition of a logarithm and an exponential, right? That's why when you take the composition of the log of the exponential, you get x. When you do the exponential of the log, a to the log a, you get x, because they're inverses of each other. Okay, now, on this graph right here, I've got, this is the y equals 2 to the x, right? This is the y equals log base 2 of x. And you could tell they've highlighted a few points here, right? And for every point on the exponential, if you flip the x and the y coordinates, you get a corresponding point on the logarithm. And especially important is, remember that the exponential had a y-intercept of 0, 1. Well, that means the logarithm has a x-intercept of 1, 0. Right? Remember that the exponential had an asymptote of the x-axis, y equals 0. Okay, well that means that the logarithm has an asymptote on the y-axis, which is x equals 0. And then again, domain and range. It should be, since this thing had a domain of, the exponential had a domain of all real numbers, all reals, then the inverse has a range of all reals. Since the exponential had a range of y greater than 0, and the inverse has a domain of x greater than 0. Right? Asymptote, y equals 0 for the exponential, x equals 0 for a logarithm. Intercept, 0, 1 for an exponential, 1, 0 for a logarithm. Again, it should look like, with respect to this line, which is going right to the middle, that these two graphs are just flips across that line. Now, what the base of the logarithm is doesn't change the graph much, not in any of the important details. That's I'm just trying to show on this. One of these is log base 2 of x, and the other is log base 4 of x. You know, are they a little different? They're a little different. However, they have the same x-intercept, right? They have the same asymptote. You can see the graph approaching but not touching the y-axis. And so the domain is the same. The range is the same. So changing the base doesn't change the important details of the function. And the important details, besides all those other things, it's the shape, right? You're supposed to know what the shape of a logarithm looks like. And there's something, if you are a slave to your calculator, if you don't really understand any of these functions other than I've put it in there, I'll just say what I see on the screen, then you're going to get logarithms wrong a lot, okay? First of all, if you were presented with either one of these graphs and asked what the range is, it doesn't look like that line is going up forever, but it is. We know that the range of a logarithm is all real numbers. It looks like it's flattening out, right? But it's not. It does not have a horizontal asymptote it's approaching. Oftentimes when you get asked a test question about this, you'll try to put a horizontal asymptote there. But that line is going forever up. It's going slowly, but it'll get there, right? It's going to positive infinity. Range is all real numbers. These graphs, they'll look like the graph is stopping. I mean, on the calculator, it's stopping. The calculator cannot resolve these when they become almost vertical. It just stops drawing the graph. But the graph does not stop, and you're supposed to know that, right? Don't let the calculator tell you something that is not correct. I mean, if you put it, especially if I put it out, let's say here, watch this, clear. Let's say I did a log of x minus 2, so it's going to shift it 2 to the right, and then I'm going to add 3. I'm going to hit graph. Let me do second stat plot, 1, turn that off, then go back to 6. See what that looks like? I shifted the graph 2 to the right, and it looks like it stopped. It does not stop. It has an asymptote here, and as graphs do when they approach vertical asymptotes, they go forever, either to negative infinity or positive infinity. The graph does not stop. And when you just write that as your graph, that's the indication you actually don't know what a logarithm looks like at all. You just put it in the calculator. So you got to know more than the calculator. Now, another thing I was going to tell you, it'll wait till next time. It might be more appropriate for the next graph, the next lesson anyways. This is just giving an example of a couple shifts, right? And what changes when you shift the graph of a logarithm. For example, this one here on the right, it's got both the log of x, base 10, right, here, and the log of x minus 1. Okay, well, what do we expect happens to a function when you subtract inside the function? It goes to the right one. So if I take this graph, the gray line here, and I move that whole graph to the right one, that not only moves the graph, it moves the asymptote. So now you got a new asymptote, which is here. Okay, everything went 1 to the right. Okay, so now what do you think is the domain? It used to be x greater than 0. Now it'll be, if the whole graph moved to 1 to the right, x greater than 1. Okay, if the x-intercept was 1, 0, you move the whole graph to the right. Now it's at 2, 0. So moving a logarithm graph horizontally, left or right, is going to change some of the important details of the graph, specifically domain. Okay, and now we see what happens if you add a number not inside the function, but outside the function. Generally, that's a vertical shift. Plus 2 means up 2. Right? So if I started with a graph of the log x, and it had an asymptote at x equals 0, would that line change if I moved it up or down? You take a vertical line and move it up or down. It's still the same line, right? So the asymptote. So if the asymptote didn't change, the domain didn't change. Now, did the intercept change? Sure, you moved every point on this graph up 2. Now you don't have, if that's at 1, 0, now it's at 1, 2. Right, that point went up 2. The x-intercept is somewhere over here, and it would take things that we're going to learn later in the chapter to figure out exactly where it is. Okay, now remember E. Okay, we've dealt with E already today in the homework. E is called the natural base of an exponential, but we also have logarithms which have a base of E, right? Log base E of x. And if it is log base E, you don't write log base E, you write ln. ln means natural logarithm. If E is the natural base, ln is the natural logarithm. Now, you can see there's your log on the calculator. Look right underneath it, ln. Right, those are the 2 most used logarithms. In fact, ln is used way more than log base 10 is. You get into serious math and science classes, you're probably not using log base 10 hardly at all. You're always using ln. I mean, it's so much so that when you're in like higher level math and science classes, if somebody says logarithm, it's assumed you mean natural log. I mean, there's always a few examples that they'll give for log base 10, like the Richter scale for earthquakes, that's certainly a log base 10. Sometimes decibels is a measure of audio, how loud something is. But for most things in math and science, it's ln. And so when you see an ln of x in your mind, you've got to be thinking, oh, base E, base E. Getting there. You're done. Okay. So the properties of natural logarithms are the same as the properties of log of any base. Wouldn't they have to be? The properties we already saw said they were valid for any base, A, right? Okay, well now A equals E. So the only thing that's going to change now is that instead of saying log, you see ln. ln of 1 equals 0. Right? We already said that you take the log of any base of 1, you get 0. So it's still true. ln of E, well, that's matching the base and the exponent, base and the number that's inside, so it's 1. ln of E to the x, and that's the inverse. That's taking a composition of a function and its inverse. And of course, that simplifies to x. And it doesn't matter the order you take that composition, ln of E to the x or E to the ln of x, either one, they cancel each other out and you get x. So again, using those properties, right, which property would we use to simplify ln of E to the 1/3? Which property is it? ln of E to the x equals x. ln of E to the 1/3 equals 1/3. Right, that's this one. Okay, how about 5 times ln of 1? Forget about the 5, right? What's ln of 1? ln of 1 equals 0. So this is going to be 5 times 0, which is 0. That's this property. So, go ahead. 3/4 times ln of e. Let's see. Okay, thank you. Okay, again, forget about the 3/4. What's ln of e? Which property is that? The second one. ln of e is 1. So this is 3/4 times 1, which is 3/4. That is this property. And how about the last one? E to the ln of 7. Which property is it? It's the second part of the third property, right? Again, this is the composition, just switching the order. So e to the ln of x equals x. E to the ln of 7 equals 7. That's this one right here. Okay, again, for ln, things are pretty much, it's the same as logarithm, right? The basic shape of a logarithm graph and an ln graph, it's the same thing, right? Is it a teeny bit different, like the difference between ln of 2 and ln of 4? Sure, a little bit, but all the details are the same, right? So if I subtract 2 inside of a logarithm or inside of a function, the shift is right 2. Right 2. So does that move the asymptote? I mean, they've already moved it for us, but yes, everything got moved 2 to the right. So what is the new domain of that function? Used to be x greater than 0, now it is x greater than 2. Right? Don't say x is greater than or equal to 3 or something like that, right? You'd be missing all the points in between 2 and 3, all those points here. This one has got a couple of different things going on. It's clearly been shifted to the right too, but it's also been flipped because it's got a negative in front of the x, right? What does it look like the domain of that is? How about x is less than 2, right? The x values are to the left of 2. There's nothing over here. And how about this next one? Notice this one, ln of x squared. Remember, you can't take the logarithm of a negative, but if you're squaring what's inside, everything's either positive or 0, right? There's only one value now that cannot be plugged in for x, and what is that? 0, because you can't take the ln of 0. Right, so that's why this graph has got 2 branches. Right? One of them is the typical logarithm-shaped graph. And then, because you can actually put in negative values of x, you get this branch too. But neither one of those touches the the y-axis. Right? They still has an asymptote at x equals 0, which means the domain is x does not equal 0. It could be anything else, it just can't be that one thing. And one last property, okay, problem. So again, at this early part in the chapter, we don't know how to solve equations yet, other than the simple one-to-one property. So the word problems are not involved with solving equations. They're mostly involved with evaluating, meaning plug in. Just plug in and calculate, that's it. So this one is example 11, human memory model. Students participating in a psychology experiment attended several lectures on a subject and took an exam. Every month for a year after the exam, the students took a retest to see how much of the material they remembered. The average scores for the group are given by the human memory model, right? The model means it's a mathematical equation that's supposed to represent this. So here's the human memory model. F of t, right, equals 75 minus 6 ln of t plus 1. Right, what is this thing afterwards? 0 less than or equal to t less than or equal to 12. It's kind of like when we did the piecewise functions. What was the thing that followed the function? Domain. They're telling you which values you can plug in. Right? So it looks like since we are dealing with t is time in months, it looks like we can plug into this formula from t equals 0, means at the beginning, and t equals 12 after 1 year. Okay, so what was the average score on the original exam? How would you find the value of this function? And they've told you in parentheses, t equals 0. How are you supposed to find the value of the function? Plug in 0 here and just calculate. I mean, in this case, if you put in a 0 for t, 0 plus 1 is 1. What is ln of 1? It's 0. So at the very beginning, this term right here is all 0. And the value of the function is 75. Okay, now that won't be true again. If I plug in 2 for t, now it'll be 75 minus 6 times ln of 2 plus 1. And that becomes 68.41. So the scores go down after 2 months, from 75 to 68. And then again for 6, I plug in, and this one is 63.32. So obviously it's going down. Okay, could you plug in for 24 months? Why not? Because it's not in the domain, right? They're telling you when you can use this function, right? And it doesn't mean like, if you plug in 12, I mean, it'll work. It'll give you a value. But they're saying this formula is not valid once you get beyond 12 months. So you wouldn't want to keep using it. So that's logarithms. You know, we did logarithms with a base of a. We did logarithms with a base of e. We should understand the basic graph and how to shift it around more than just putting it in the calculator. And at this point, this last thing is really read the word problem, evaluate. There's no solving to do yet.